This is module M5H of the Indiana Department of Transportation Certified Asphalt Lab Technician Program. And it's about the relationship of mixed design properties to performance. So the first of these pavement properties that we will speak about is rut resistance. This is someone's idea of a rut-resistant pavement. The asphalt binder is gluing the rocks together and making them resistant to deformation. So what can cause rutting or low rut resistance? Well, the first thing is excess asphalt content. And that can lead to bleeding, rutting, flushing. And here you can see an example of a pavement that is suffering from rutting and bleeding. And you can see in the wheel paths the excess asphalt that's showing up in the wheel paths. And when you look at a close-up of this, you can see the asphalt is oozing out on the surface of the road. And so there's mostly bleeding that is taking place in this example. And that was because there was a mill and fill and the lift thickness was thin. As a result, the excess asphalt that was in the mixture only allowed it to densify and squeeze the extra asphalt out through the surface, but it didn't cause rutting to take place. But in the areas adjacent to some overhead structures, they not only milled and replaced the surface, but for a couple hundred feet before each bridge, they did the intermediate layer as well. And there you can see that there's actual rutting that is taking place, not only the bleeding, but the rutting. So if we put too much asphalt binder, and that would be more like an accident kind of thing, say a plant set of calibration or something like that, we will end up then with excess asphalt binder, rutting, flushing, and bleeding. There's no washboarding on this, which was one of the other things that was on there. You might get that in an urban environment near a stop sign or something like that. Excess medium-sized sand, well, that's kind of, a code word for natural sand. So if I make a mixture that has a very high percentage of natural sand in it and it's subjected to heavy traffic, it will tend to move around. So here's an example of where this played into a pavement problem. And this was on a city street that connected to a state highway, which you see here. The city street goes into the slide or into the distance. And there's an interstate highway back up here that you can't quite see. Sorry, I'll change there's an interstate highway that you can't quite see. Here's the state highway here, and then the city street heads off in that direction to a truck stop, which is 1,500 feet down the road. So this got paved with a regular hot mix asphalt, and after 2 years in service, this is what it looked like. Not very good. Now, there were signs of rutting that were showing up almost immediately during construction. In fact, before construction was over. And the question was, what might be causing this? And so, and whether or not the hot mix asphalt could stand up to these slow-moving trucks. So what the contractor did was build a trial section right before the traffic light, and using the AASHTO specifications for this, by the way, predated the implementation of SuperPave by the city, but the DOT was using SuperPave, And so the suggestion was, why don't we build this using super pave specifications? And that's what was done. After 2 years, we came back and found almost no rutting anywhere on this. And of course, the rutting that we see on here is about 2 to 3 inches. Now, here's the scenario of what's happening when hot mix asphalt is rutting. So the worst location for rutting is along the edge of the tires and down about 2 inches from the surface. So I have a university professor to thank for this slide. And you can see that they did some modeling of stresses that are being subjected, that the pavement materials are being subjected to from this truck. And the HMA is 6 inches deep or thick. On top of that, 12 inches of aggregate base. And the thing that you'll notice here is this kind of this edge here. And this is about 2 inches down along the edge of the tire. That's the point of maximum shear force. And it's a shear force that's going out at a 45-degree angle. The tire is coming down and trying to push that mix upwards and outwards. And that it's exactly that shear force that is, or shear stress that is causing the rutting to happen and to have that hump along the edge of the wheel path. Now, the key thing here is that it's a sign that the aggregate skeleton in this mixture is too weak to carry the shear forces that are being imposed upon it by the trucks. So one of the things that we did in investigating this was to measure the shear stiffness of the mixtures. And this was the original mix that was placed. This was the super pave mix that was placed. And so what do we know is that 75,000 psi of shear stiffness is sufficient to stand up to the shear forces that are being applied, whereas 23,000 psi is not. So what the DOT did, the city did, is come back and after the second year, they let a contract and they repaved. And I took this photograph 9 years after they had repaved, and you can see that the pavement is really performing very well. For 9 years old, there's very little cracking in it and almost no rutting, certainly none that's visible to the eye. Now, the issue here on this project was really an issue of specification, a problem with specifications, because what had happened was that the contract that this project was located in was a contract that was a bunch of miscellaneous pieces of streets around the city. And so you had, a block where a water main was replaced, and you had a couple blocks over here, and all these different city streets. And oh, by the way, you had this 1,500 feet of road that went up to this truck stop back from the light, which is back behind where I've taken the photograph. And they just called for the same mixture in all situations, that mixture being a residential street mixture. Well, that residential mixture had about 35% natural sand in it. For a residential street that gets a garbage truck once a week, perhaps a school bus twice a day for a couple hundred days a year, the odd delivery truck, it works perfectly fine. But if we put it under 2,000 Class 8 trucks, 18-wheelers, traveling at about 10 to 15 miles an hour, it doesn't work very fine. And that's what we found out. So the second pavement property that we will talk about is pavement durability. And what is durability? By durability, we mean the ability to stand up under the baking action of the sun and in the presence of moisture. So what can cause poor mix durability? Well, the number one thing that will influence durability is low asphalt content. So if we design mixtures that are too dry, they will end up aging more rapidly and they will end up raveling. So it's actually on a county road, but it's a pavement that's about perhaps 8 years old. And then all of a sudden, in the course of one late spring, late winter, early spring, the pavement, the wearing course completely unraveled. And essentially what's happening is the low asphalt content allowed the oxygen to get in and to age the asphalt binder. When it was aged sufficiently, then rocks started to get dislodged. And as soon as one or two rocks started to dislodge, adjacent rocks then could easily be torn out by the traffic traveling over it. So if you look at that rock right there that is sticking up, you know that it won't be too many more vehicle passes before that rock will be knocked loose. And where does it end up? Well, right here, along with all these other rocks over on the shoulder of this county road. Now, another way that the asphalt pavement can age very rapidly is high in-place air voids content. So if we have a good mix, but we leave it with high air voids, meaning it has high permeability, then what happens is, once again, the oxygen can go into the pavement, it can age it, and then it ends up causing poor mix durability. So here's an example on an interstate. Now, this interstate had some patching that was done to it using milling. So they'd gone in and they'd milled the surface course, and these milling patches were full lane width, and they were anywhere from maybe 100 feet long to a quarter-mile long. And they were scattered along, I forget, about 50 miles of roadway. Quite a long distance. I don't really remember. Now, I had seen an example of this, and I wanted to take a picture of another one, and there I see it. And so I was ready with my camera, and I took a picture of it. There's the butt joint of a patch. There is the patch there. So they milled the full lane width and they replaced it. Now, what I wanted to do is I wanted to take a picture like right here so that we could see the very edge of this patch. Well, it kind of didn't work out, and the picture that I took was just past it. But here's the thing that I want you to pay attention to. So I'm just a few feet past where that butt joint is, and this spot here, I don't know, that's maybe 75 feet from the butt joint. The trailer here is about 50 feet long. And you'll notice that there's no crack here, and there's a crack here. And you'll notice the wetness up by the butt joint, and that wetness disappears. Well, what's that wetness all about? Well, that wetness is high permeability. Now, I would make the argument to you that in the 75 feet from back at the butt joint up to where my cursor is sitting, that there's likely very little change in the mixture properties. It is the same mix. Asphalt content, gradation, all that stuff is the same. What's different about back by the joint and up here where my cursor is, or my pointer is? The difference is in-place air voids. So where the air voids are high, the water can get in and aging can happen. Well, what else do we see? Here's a crack. And then this crack disappears. Why does it disappear? It's because the density is higher, the permeability is low, and the pavement did not age. So this slide gives you an example of what happens when we have high in-place air voids or low density. By the way, end of the patch, same thing. There was also a couple of other spots that I noticed along here that I took pictures of, and it's the same issue. Although we're not seeing cracking here yet, we definitely can see differences in permeability. So the permeability here is lower than the permeability here, and the permeability on this side is higher than on this side. And what happened here? I don't know. I can only speculate, but I can say one thing for sure, and that is the fact that this pavement with higher in-place air voids will start to fail and come apart faster than these areas that have lower in-place air voids. So the next property that we'll look at is workability. So workability is the ability to place and compact a hot mix. So one of the things that can cause poor mix workability is a mixture with very large maximum size particles. So this mixture, I'm showing a belt sample at the hot mix plant, has twos in it, meaning that it has a maximum size of about 4 inches, a nominal maximum size of 2.5 inches. So there's only been one time ever in my life I've seen a mixture with this large of a nominal maximum size. And what was that all about, or why was that? Well, first of all, here's the truck that is dumping the mix. So you can see what the mix looks like in the truck. You can see what the mix looks like in the hopper of the paver. And you can see what the mix looks like on the road. Now, this was a 9-inch single lift of hot mix. And because there was no handwork, it placed well and it compacted well. Now, there was not a density specification on this job, but it certainly did roll and appear to compact well. Now, this is on a private facility, and it's in an industrial location. And this piece of roadway is designed to carry, will carry 300,000-pound loads. And so because of these heavy loads, it was a thick pavement structure, and the base course called for a very large nominal maximum size aggregate. Now, even if the mixture doesn't have large aggregates in it, if it has excess amount of coarse aggregate, in other words, if it's a very coarse graded mixture, it will be difficult to compact. In the 1990s, when Superpave was first being implemented in Indiana, everybody was of the opinion that these coarse graded mixtures, such as you see right here, were desirable. That was the best way to design a mixture to be rut resistant. Well, we discovered, or we determined, that it did not have to be coarse graded to be rut resistant. But when we tried doing some of these mixtures, what we ended up with was problems. And the problem was that we could not achieve density. So here we are on an interstate highway. The project has called for milling the existing overlay down to the old concrete and placing an intermediate layer and a surface layer on top of it. So they've been placing this 19mm intermediate layer that I just showed you the picture of the gradation of. They've been putting 14 passes of the roller on, trying to get density. They sort of are getting density, but it's kind of like marginal. So sometimes it passes, sometimes it fails. And clearly they're breaking aggregate. And so the thought was, hey, hold on, we can't compact this new mix. It is not compactable. So what we did is said, okay, well, let's try and see if we can figure out how to compact this. And one of the things that we decided to do is to slow down the rollers. Now, you might think, based upon that, that perhaps the rollers were moving too fast. They indeed were not. The typical rolling speed is about 3 miles an hour, which is just a nice, comfortable walk speed. And the rollers were running about 3 miles an hour. But we said, well, hang on. Let's reduce the rolling. Let's cut it in half. Let's roll it about 1.5 miles an hour. And of course, the reaction of the superintendent was that, hang on, I didn't budget for that many rollers. I'm going to need more rollers out here. Who's going to pay for all these rollers? And I said, well, hang on. Let's just try it first of all and see what happens. Now, here we are. There's the patch before. Here's the part that we just compacted. We finished compacting. First thing that you'll notice is we have not turned the road totally white. We've used a non-nuclear gauge to measure density, and we get a gauge reading directly coming out from under the screed, and we get a 2.205. First pass of the roller, we get 365. So we went from 205 to 365. Big jump in density. Another pass, 369. Almost nothing. Okay, so let's do 2 breakdown passes. Let's let the temperature come down about another 50 degrees, and then we'll do the intermediate rolling. First pass of the intermediate roller, which again was a vibratory steel compactor, and it goes from 369 to 416. Pretty good jump. 416 to 454. Pretty good. 454 to 475. Still good. 475 to 423. Oh, hold on. It broke. Okay, so we're not going to put this pass on. What do we need? We need 2 breakdown passes and 3 intermediate passes, and then we're ready for finish rolling. So 5 passes. By slowing the roller down, we were able to accomplish passing density. Oh, I forgot to mention that the densities were about 1% higher than they had been back there where we used 14 passes. So we were able to achieve a higher density, only use 5 passes at half the speed. So actually, to tell you the truth, we had more rolling power available on the job than what we needed. So we didn't have to get any extra rollers. Now, this picture was taken back in the 1990s. And today, we probably wouldn't address this issue this way. And why is that? Well, from a practical point of view, you know how slow 1.5 miles an hour is. I mean, it's just like a slow walk. And so literally, don't tell OSHA I said this, but you could get off the roller and walk at a normal rate 100 feet up the road and wait for your roller to come and meet you and then get back on the roller. So it's just so slow that it's just boring. So what we would do today is we would adjust this mixture to be less coarse than what it is. But if we have very coarse mixtures, workability and specifically getting compaction is going to be an issue. What else can cause poor mix workability? Well, excess sand. Now, the problem here is not that the mix won't compact because it's just resistant to compacting. The problem here is the mix will not sit still underneath the rollers. So here you can see the paver. There's the joint going here. The roller's gone up and back, and you can see these marks that they've left on the pass right beside. And this was in a parking lot, in a commercial shopping center parking lot. And you can see all these marks on here. And of course, you get these short transverse cracks, and you can't roll them out. The more you try and roll them, the bigger they get, and it's like, hold on, time out. Well, what's the problem here? The problem is excess natural sand. And the consultant that was representing the owner of this parking lot was from a different state, and the owner of wanted something that had not very much texture, so they wanted a high sand content, and the consultant was used to using sands from their home state, which worked quite well, but Indiana sands did not. They were too rounded, and so as a result, the mix would not sit still. The fix was redesign. You know, figure out what was acceptable that could be left in place, what had to be removed, go and do another mix design, still fine graded, still tight texture, but now more manufactured sand in it and less natural sand than what had been. Now, you can also get tenderness or workability issues after the fact. And here you've got a lumber yard in a small town, and the local service club, the owner of the lumber yard said, man, they'd really like to pave their yard and get that stone lot, dealing with the stone and that they and the contractor, who's also a member of the service club, said, well, I can produce you a very low cost mix, and it had lots of natural sand in it. And the issue was that all these tearing marks come from that forklift right back there. And so you get all these marks and divots, and as you can see, there's very little rock in this mixture. It's mostly composed of sand, which is a weak aggregate skeleton. The other thing that can cause poor mix workability is high filler content and low filler content. Back when we were talking about doing mix design, we talked about the fact that there's a fairly narrow ratio between the minimum and the maximum on the percent passing the 200. Well, on the job, if we, at the hot mix plant, if we don't control the return of baghouse fines back into the mix as well as we could, what can happen is we can get a non-uniform distribution of fines in the mix. Basically, we can starve the mix, and now it looks very rich and bright and shiny, and then you get a slug of baghouse fines that will go in, and the mix will, instead of being shiny, will be a dull color, and then it'll turn shiny again, and then it'll turn dull. So when the filler content is high, it'll get dry and gooey and gummy, and when the filler content is low, it can be tender, it can move around, and we can get drain down. The next property that we'll look at is fatigue resistance. What can affect fatigue resistance? First of all, what is fatigue? Well, fatigue is the phenomena where you can cause a material to break even if you don't load it up to its maximum tensile strength. So if you think about a coat hanger, and you're going to roast some marshmallows, and you find this coat hanger, and you undo the top, and you kind of straighten it out, but now in the end, you've got this twisty thing that you got to get rid of. Well, how can you get rid of it? Well, there's no one who's strong enough that you can say, let me just pop that baby right off for you. What do you do? Well, you take that coat hanger at the end of it, and you bend it down 90 degrees, and you bend it up, and you bend it down about 3 times, and it breaks. Now, you never ever loaded the steel in that coat hanger up to its maximum tensile strength, and yet you got it to break. That's fatigue. So if you think about a pavement, it flexes underneath the loads. Now, the flex is not so great that you can see it. You can't see it with your eye or anything. But that tiny bit of flexing means that you're putting it, you are causing some fatigue damage to it. Now, think about that coat hanger. And if instead of bending the coat hanger 90 degrees, let's say you got to bend it 1 degree, 1 degree down, 1 degree up, down, up, down, up, down, up, down, up, absolutely guarantee you the campfire will be out before the coat hanger breaks. Okay, but it will break in fatigue. So that's kind of the situation with a pavement. A pavement is designed, if it's designed to carry, let's say, 10 million easels, equivalent single axle loadings, the thickness of the pavement is designed in such a way that the amount of deflection is such that it should carry at least 10 million axle passes before it breaks in fatigue. So that's fatigue. So what can cause fatigue to occur? Absolute number one thing, low asphalt content. So if you think about an asphalt pavement that's, let's say, designed to carry 10 million repetitions before it breaks, if you could add another 0.6% asphalt binder to that mix. Now, you can't just dump it in. Okay, if you just dump it in, what's going to happen is you'll end up with rutting and excess asphalt. You have to design it in. You have to change the gradation, the aggregate skeleton to make room for it. But let's say that you do that. The 0.6% additional asphalt will allow that mix to carry 3 times the number of passes before it breaks in fatigue. So instead of 10 million, 30 million. Now the flip side is true too. Let's say that you reduce the asphalt content by 0.6%. You will cut the number of axle passes by about a factor of 3. So plus or minus 0.6% asphalt binder means you can go from 30 million axle passes before it breaks down to 3 million or 3.3 million axle passes. It's huge. It's incredibly sensitive to it. Now, the high voids content just means that the asphalt binder ages more quickly, and as a result, it can't stand as much flexing as it used to, and so it'll crack prematurely. So if we leave the mix with high in-place air voids on the road, we end up with cracking that will happen. Lack of compaction is just both of these is a way to have high in-place air voids. And then the last one is inadequate pavement thickness. It's not too often that we're going to run into this as a problem, but you know, if a customer comes to a contractor and says, you know, I need this pavement built, and here's the traffic that I anticipate is going to go on it to get to my building, and the engineer comes back and says, well, you need 8 inches of hot mix. And it's like, ooh, yeah, that's more money than I really have. And say, well, you know, could we do it with 5 inches? And the answer is yes, you could. Now, it'll work, and it'll work fine for a while. What's happening with the 5 inches? The 5 inches is it's going to bend more as compared to the 8 inches where it's going to bend less. So it's like the coat hanger. The more you bend it with each time, the faster it breaks. So here's some examples of fatigue cracking. Now, I didn't take this picture, but this is a rural highway that's got some problems with drainage. And so even though this picture was taken in the wintertime, I'm certain at some points in the year, there is water that ponds in this ditch, and that water is soaking in underneath this pavement and softening the subgrade. So why is it cracked here and not cracked here? The difference is the amount of deflection. It's the coat hanger thing again. Now, I did take this picture In this picture, this pavement, it's a private pavement at a truck stop. And that you are looking at a 3-year-old pavement that is 10 inches thick. And it is fatigue cracked all the way through. And not only is it fatigue cracked, but you can see mud that is pumping up through it. Well, it turned out that this was a brand new site for this truck stop. And what was not recognized at the time of construction was that there was groundwater in this area. And so what's happening is the subgrade became very soft, and as a result, we had very high deflections, and it failed in fatigue. Fatigue is a critical failure because it's an expensive failure to fix, because you can't just come in and mill it flat and put 1.5 inches or 2 inches on top of it. If we tried to do that here, it would last 2 years, perhaps, under this traffic. What's the fix? The fix is remove and replace. So that meant removing all 10 inches of this hot mix. In fact, what they did is they put under drains on here, and then they had a French drain, and there's a creek back in the woods back there, and they built a channel to carry the water from the under drains back to that creek. But a total reconstruction of this entranceway coming into the truck stop. The last property that we will talk about is friction. And friction is the ability to stop in wet weather. Dry weather, friction is never an issue. On dry pavement, regardless of the condition of the pavement, you'll be able to stop 60 miles an hour to 0, not allowing for the reaction time, but the actual braking time, I think is a little over 100 feet. But on wet weather, you can expect that to increase maybe more in the order of 130 to 150 feet. Well, and poor friction increases the stopping distance. So if I have excess asphalt, and what happens is when the pavement is dry, I don't have any trouble at all stopping. But if this pavement gets wet, my tires are going to slip on top of this asphalt. And maybe I should have used that picture that showed the bleeding on the interstate highway that I used earlier in the presentation. But even given that, you can imagine if I was negligent and driving along at 25 miles an hour in this parking lot when it's wet, when the pavement is wet, and a 5-year-old darts out from behind that pickup truck there, and I slam on the brakes, it could be a not too good of a situation, whereas in dry weather, it would be a non-issue. The other thing that can cause it is smooth aggregates. Now, these can be smooth either because I used very smooth aggregates originally, no crush count and smooth polished gravels, or an aggregate that polishes, like a limestone. So what happens with limestone is that it does not have a crystalline structure. And so as a result, it will, as it wears, and limestone is not like super hard, it's just kind of like the better grades of limestone are medium hard. And so what happens is each vehicle that goes across there is wearing on top of the rock. I took this picture, it was a trial section on an interstate pavement, 10 years old, and the objective was to see if we increased macro texture, in the wheel path, could we use limestone as our aggregate? And you can see this is a mixture of limestone and slag in here. Now, this is 10 years old, and these aggregate particles are worn down flat. That looks like a little paving stone, all of the aggregates are worn down flat. They were not flat originally, but they are flat and they are smooth and they have low texture. So the reason why this pavement was milled and replaced was not because it failed in cracking or rutting or anything like that. It had to be removed because it was no longer safe in wet weather. So the point that I want to make to you is that pavement properties, there's kind of a balance, and basically all of the properties must be considered. You can't just do one and not do the other. So let's look at kind of the big picture view of the relationship of these pavement performance, to the various different things that we put into our mixes. So the high temperature grade and low temperature grade of our asphalt binder, the coarse aggregate angularity, fine aggregate angularity of our aggregate structure, of course, the gradation of our aggregate structure. Then the volumetric properties, the air voids, and these are the in-place air voids, the effective asphalt content, how much asphalt is in it, the VMA in place on the road, and the voids filled with asphalt on the road. So let's look at rutting, and let's look at which of these properties influence the rut resistance or the resistance to rutting. And the answer is mostly the aggregate skeleton, almost completely. But here's the thing about aggregate skeleton. You can have very good quality aggregates. And if your in-place air voids are very low and then your voids filled with asphalt become very high, and basically it'll turn plastic on you. The best example that I can think of to demonstrate this to you is if you go to a lake on a nice summer's day and you walk on the sand, or if you go to the ocean and you walk on the sand, a nice sandy beach, and you're just up above where the water is. So the sand is saturated with water, but you're not in the water, so there's no free water standing on top of it. Now you can walk down the beach and you'll leave little indentations from your footprints, but basically the sand holds you up. Now, that sand is saturated with water, and the sand itself is very rounded particles. Now, if you stand there and you take your foot and you lift it up, and then you just press down, and you lift it up and you press down, and you lift it up and you press down about 3 or 4 times, and you're going to notice that you start sinking down into the sand. What just happened? Why did that happen? Why did it hold me up at first, but then it doesn't hold me up after I put a repeated load on it? It's because the pressure from my foot is building up in the water in between the sand particles, pushing the sand particles apart. That allows the aggregate skeleton to disintegrate, and now I sink into the sand. Well, it's not exactly the same thing, but it's kind of the same thing on an asphalt pavement. If I saturate it, completely saturate it with asphalt binder, then what happens is the truck tires come and they put a load down and take it off, and then another truck tire comes and puts a load down. Now, it doesn't disintegrate the skeletal strength of the asphalt pavement as severely and as quickly as it does at the beach, but it will, and that can cause the rutting to take place. So and that's partly controlled by the by the VMA. And some years ago, they used to think that, well, if I just use a harder grade of asphalt binder, it'll be more resistant, and I put the more rut resistant. And I put this here as a dashed line. That's because if I've got a good aggregate skeleton, using a higher PG grade will give me more rut resistance. So for example, a PG 76 asphalt binder should produce more rut resistance than a PG 64 asphalt binder. But that's with the condition that it's not totally flooded and saturated with asphalt. if it doesn't have, and that it doesn't have, let me back up. If it has a weak aggregate skeleton, I cannot fix it with a PG high grade. You know, you can do a PG 102 maybe, but I don't think you can buy such a thing, and you probably can't mix it hot enough to get it put down. But yeah, so basically, a high temperature grade only has a moderating effect on it. Well, what about fatigue cracking? Well, I've already talked to you about asphalt binder content, or the effect of asphalt binder content, and that's being the big one that controls fatigue behavior. There is also some relationship to PG low temperature grade, like a -28 is not quite as susceptible to fatigue as a -22, but I mean, it's not a night and day kind of thing. It's not dramatic. So whereas the asphalt content is very dramatic. What about low temperature cracking? That's the transverse cracking that happens in the wintertime, almost exclusively controlled by the low temperature properties of the asphalt binder. If I try and use a PG -22 asphalt in I don't know, northern Michigan, where it's a -34 grade needs to be used, it's just going to shatter. Okay? It doesn't matter what the gradation is. Now, asphalt content has a little bit of effect on it. If I was to make a design that had a very high asphalt content, it'll make it a little bit more resistant to low temperature cracking, but it's not going to dominate. The main thing that's going to control it is the low temperature grade of the asphalt binder. Now, we showed some pictures of aging earlier on. The number one thing that affects aging is the in-place air voids. If the air can get into the pavement, it can age the asphalt binder. Now, how does the air get into the pavement? Well, if you let's say we have high in-place air voids, and what happens in the morning is the sun comes up. So the sun comes up, and the pavement starts to get hot. Air that's in the pavement expands, and some of that air gets pushed out into the atmosphere. Sun goes through the day, descends at night. Now what happens? Pavement cools off. What happens to the air inside the pavement? The air cools off, and it shrinks, or it constricts. So now what happens is it sucks air out of the atmosphere into the pavement. Tomorrow morning, the sun comes up, and now what happens is the pavement heats up and air gets expelled, sun goes down, air gets sucked in. So every day air gets pushed out, new air, read new oxygen, gets sucked into the pavement, and that oxygen causes the asphalt binder to age and become brittle. Now, you can have an effect on the aging by increasing the asphalt content. Now, this is one of the things to keep in mind. Can I make a pavement more durable, more resistant to aging, just by increasing the asphalt content, just by increasing the effective asphalt content, VBE? And the answer is not really. If I build it to the same in-place air void as what I had before, then it will age. It turns out that oxygen can by permeate can go through a film of asphalt that's 300 microns thick. That means it's 0.3 millimeters thick. That's thicker than the films of asphalt that we have in a hot mix. Our films of asphalt in hot mix asphalt, depending how you calculate it theoretically, are somewhere around 8 to maybe as much as 12 microns, nowhere near 300 microns. So if I was to increase the asphalt content and increase the film thickness from 8 microns to 12 microns, that'd be 50% increase in film thickness. It's still permeable to the oxygen. It's still going to be susceptible to aging from the oxygen. Now, the thing that I want to point out to you about this is that we control all of these performance properties using the material properties and the volumetric properties of our mix. But the one thing that you'll notice that there is no arrow to is gradation. Why is that? Well, it turns out that rutting, you can have a coarse graded mix or a fine graded mix and have it be rut resistant. Fatigue cracking, it doesn't matter what the gradation is, coarse graded or fine graded, and it can resist fatigue cracking. Low temperature cracking is from the asphalt binder, it has nothing to do with gradation at all. And aging has everything to do with the in-place air voids content. Whether it's coarse graded or fine graded, doesn't matter. So, but gradation is very important because gradation is how we control these volumetric properties. So we control the packing of the aggregates, and hence the VMA, and that VMA in combination with the asphalt content influences the air voids, the in-place air voids. And so VMA is very important. Gradation is very important as a result. So that's the relationship of the mixture properties to performance on the roadway. And with that, we end this video.